On this worksheet, we're going to be doing 4 stoichiometry problems that all pertain to this balanced equation right here. The first problem is asking us to calculate the theoretical yield of CO2 from 2.15 grams of CH3OH and excess O2. So let's begin by talking about some of these terms in this problem. Excess O2, that phrase, from the perspective of a student, anytime you see the word excess being applied to one of the molecules, that literally just means you can ignore it completely. Excess means, exactly what you think it means. It means that we have a lot of O2, we have a ton of O2. We have more O2 than we need, and therefore we do not need to take it into consideration at all. So when you see that, that just tells you that we're going to disregard the O2 completely in this problem. Theoretical yield is another way of asking us how many grams. So when you see what is the theoretical yield, that's just a fancy way of saying how many grams of CO2. We call it a theoretical yield because it is representing, like, hypothetically or theoretically, if everything were to go perfect, if there were to be no mistakes or nothing like that, nothing bad happens, what's the mass, the grams of CO2 that we're going to make. So when you see theoretical yield, just interpret that as how many grams. Now, stoichiometry problems, as you know, they all involve giving you information about one molecule, 2.15 grams of CH3OH, and asking you to use that to calculate information about another molecule, grams of O2. So that's all we're going to be doing in this particular problem. We want to start by writing down the number and the unit and the molecule that has been provided to us in the problem. So that's the 2.15 grams of CH3OH. And we want to multiply that by a conversion factor that lets us get rid of that unit, grams of CH3OH, because we don't want that unit. Now, I've mentioned this several times in other videos. Whenever you have you're starting with the unit of grams of something, the only thing that you can convert that into is moles of the exact same molecule. So you have no options here in terms of what you're going to do, because we're starting with grams of CH3OH. When we're putting grams of CH3OH at the bottom of our conversion factor, our only option is to convert into moles of that same molecule. And we do that using the molecular weight of CH3OH, going to the periodic table, looking up the atomic masses of all of the atoms in this molecule, adding all of them up together. I'm just writing them down here because I have them memorized. 12 for the carbon plus 3 hydrogen atoms, each one is 1, plus 16 for the oxygen, and then 1 more for the hydrogen. 12 plus 3 plus 16 plus 1. I round my atomic masses, get rid of the decimals on there. That's 32 grams of CH3OH per mole. Now, the next thing that I want to do is get rid of that moles of CH3OH unit, and now is where I want to start paying more attention to the problem. What molecule am I trying to solve for in this problem? I'm trying to solve for CO2. Now, you can never go from moles of one molecule into grams of something completely different, like grams of CO2. That's never allowed. Whenever you're going from one molecule to a different molecule, you have to do that in a mole to mole conversion. That's just one of our stoichiometry rules. And we fill this conversion factor in using the coefficients from the balanced equation. The coefficient for CO2 is 2. The coefficient for CH3OH is also 2. Again, that comes from the balanced equation, and that's going to allow us to cancel out that moles of CH3OH unit. The last thing we're going to do is get rid of that moles of CO2 unit and convert into grams of CO2, also using the atomic masses. So this is going to be 12 plus 16 plus 16, which is 44 grams per mole, and leaving us with the units of grams CO2, which is what we're trying to solve for in this problem. 2.15 divided by 32 times 44, because I'm leaving out the times 2 divided by 2. That gives me 2.96 grams of CO2. That is my theoretical yield. Question number 2 says, if the actual yield of CO2 is 0.655 grams, what is the percent yield of the reaction? So this is saying, okay, we did the reaction and we ended up actually making 0.655 grams. So something went horribly wrong because we should have made 2.96 grams. We just didn't come up with that much. What is the percent yield? The equation that we use to calculate the percent yield is to take the actual yield, I'm just going to write ACT, and divide it by the theoretical yield. And then to turn it into a percentage, we're going to multiply it by 100. So this problem is telling us the actual yield is 0.655 grams. We calculated the theoretical yield in problem number 1, 2.96 grams. Multiply it by 100 so that it's a percentage. And we have 22.1% yield. Not great. Let's take a look at the problem number 3. So this problem looks pretty similar. This says, what's the theoretical yield? Remember, we're going to interpret that as how many grams of H2O if we have 2.15 grams of CH3OH and 3.03 grams of O2. Ooh, so there's no excess in this situation. So this one's a little bit trickier. It's a stoichiometry problem, and remember, we have been given a piece of information. We've actually been given 2 pieces of information. We've been given a starting point of 2.15 grams and also a starting point of 3.03 grams, and we're being asked to figure out how many grams of H2O we could make. So this is actually a 2-part problem. When you've been given 2 different starting materials, you actually have to solve this problem in 2 parts. We're going to do part 1, the calculation for CH3OH converting into H2O, and then part 2 is going to be this conversion right here, and we're going to compare the 2 to each other. So again, this is like 2 totally separate problems. We'll start with the 2.15 grams of CH3OH. We want to multiply by a conversion factor that will let us get rid of the grams of CH3OH, and remember, when we're in this mode, our only option is to convert into moles of that exact same molecule. And we've done this before, so let's go up here to get that conversion factor, 32 grams per mole, so we don't have to redo that part. And then our next step, we want to convert out of the units of moles of CH3OH. And we want to, remember, we're just focusing on this part of the problem right now. We want to convert into moles of H2O because we're trying to figure out the H2O. And that conversion factor comes from our balanced equation. The coefficient for H2O is 4, and the coefficient for CH3OH is 2. The coefficient for H2O is 4, and the other one was 2. So there's that. And then our last step, we're going to get rid of that unit of moles of H2O and convert into units of grams of H2O. And we'll do this using the atomic masses, 1 for the hydrogen, 1 for the other hydrogen, 16 for the oxygen. That's 18 grams per mole. And now it's time for the calculator. 2.15 divided by 32 times 4 divided by 2 times 18 is 2.42 grams of H2O. So what we just did there was this calculation, pretending like this isn't even part of the problem. If we converted 2.15 grams of CH3OH into grams of H2O. So our next job is to do the second part of the problem. Ignore the information that we have about CH3OH. And now the problem is saying we're starting with 3.03 grams of O2. How many grams of H2O can we make? So again, like I said, 2 totally separate problems, or we have to treat it like 2 separate problems. So if we have 3.03 grams of O2, step 1, if we're trying to get rid of units of grams of O2, the only option we have is to convert into moles of that exact same molecule using the molecular weight. Oxygen is 16, and there are 2 of them. 16 times 2 is 32. Now we need to get rid of the units of moles of O2. We want that mole of O2 unit to cancel. So we're going to get rid of the units of moles of O2, and we're going to convert into the unit that we're trying to solve for in this problem, moles of H2O. These conversion factors for this step is going to come from the balanced equation. We need to reference that. H2O is 4 and O2 is 3. Those are the coefficients. H2O's coefficient is 4, O2's coefficient is 3, and then we need one more step to get rid of that unit of moles of H2O and convert into the units of grams of H2O. That's 18 grams per mole. We'll double check that our units are lined up correctly and do the calculator. 3.03 divided by 32 times 4 divided by 3 times 18 is 2.27 grams of H2O. So what we have done is calculated how many grams of H2O. We've calculated it 2 separate times. Only one of these is correct. They both can't be correct. The reaction is either going to produce 2.42 grams or it's going to produce 2.27 grams, but it's not going to produce both. Only one of them can be the correct number, and the only way mathematically that that's true is if we choose the smaller number. The smaller number is always the correct number. And let's think about that for a second, because I told you only one of them could be correct. If we choose 2.42, we're also automatically choosing the smaller number as well. If the reaction is capable of producing 2.42, it's also capable of producing every amount less than 2.42, which includes 2.27. So we always have to default to the smaller number. This top calculation that we did here is a lie. It is not possible for us to produce this large quantity. Again, just to keep things super simple, always pick the smaller of the two that you calculate. So you're going to come up with two numbers, pick the little one. This is the correct answer, and the 2.42 is just a lie. It's not anything. It's just wrong. The actual yield was 3.93, so what is the percent yield? So let's just do a refresher. The percent yield is going to be the actual yield divided by the theoretical yield multiplied by 100. The problem is telling us that the actual yield was 3.93, and we calculated the theoretical yield as 2.27. Now, that probably seems backwards to you. The theoretical yield is the maximum amount that we could make if everything works perfectly, but here we have an actual yield that's larger than the theoretical yield. So some students, when they see that, they just think, oh, I must have set it up upside down, I need to just flip it over. Don't do that. Trust yourself. You have set it up correctly. We have set this up correctly. Sometimes the actual yield is larger than the theoretical yield. This is not a good thing. This is a bad thing. A high number here, something has gone terribly wrong. We calculated that the problem is only capable of producing 2.27 grams. So the difference here, all that extra mass, is not H2O. It's a contaminant, it's a byproduct, or something is wrong. We've gathered up something that's not H2O, and our product is really bad. So again, higher than 100% yield, never a good thing, but it is something that is possible. So don't just automatically assume that you've set the problem up correctly, and don't automatically just flip your fraction upside down.